Measures of proportion and center. Example A, Tony ate 4 of 16 slices of pizza. What proportion of the pizza did Tony eat? As a reduced fraction, p hat, a lot of times the sample proportion is represented by p with a hat, 4 out of 16. And if we divide top and bottom by 4, that reduces to 1/4. As a decimal, we can divide. A fraction is, you can think of it as division. Fraction bar is like a division bar, 1 divided by 4, the fraction 1/4. We can divide 4 into 1. At a decimal point, 0. 4 into 1 goes 0 times. 4 into 10 goes 2 times. 2 times 4 is 8. Remainder 2, bring down to 0. 4 into 20 goes 5 times. 5 times 20 is 5 times 4 is 20. Remainder, subtract, you get remainder 0. Okay, so as a decimal, it would be 0.25. As a percent, we can move the decimal point over 2 places. 0.25, move it over 2 places, and that's equal to 25% as a percent. Percent means hundreds or parts per hundred, so 25 parts per hundred. Example B, a poll showed 44% of voters support Joe Biden. What proportion of voters support Joe Biden? As a percent, well, they give it already as a percent, it's 44%. As a decimal, percent means parts per hundred, so that's 44 over 100. If you divide, 44 divided by 100 is 0.44. The short way of doing it is just to move the decimal point 2 places to the right. As a reduced fraction, again, it's 44% is 44 hundredths. You can divide top and bottom by 4 to reduce it, and it reduces to 11 over 25. 44 divided by 4 is 11. 100 divided by 4 is 25. Okay. Example C. 60 patients out of a sample of 80 patients were cured by a new drug. What proportion of patients were cured as a reduced fraction? Well, it's 60 over 80. And you can reduce it by dividing top and bottom by 20. It reduces to 3/4. 60 divided by 20 is 3. 80 divided by 20 is 4. If you can't find the biggest number to go in, you can pick any number that goes in and reduce it in steps and get the same answer. As a decimal, well, fraction bar is like a division bar. Fraction 3/4 can be thought of as 3 divided by 4, 4 divided into 3. And 4 into 3 goes 0 times, so add a decimal point and a 0. 4 into 30 goes 7 times. 7 times 4 is 28. Remainder 2, bring down to 0. 4 into 20 goes 5 times. 5 times 4 is 20. Remainder is 0. So as a decimal, it's 0.75. And then as a percent, move the decimal point over 2 places. 75%. Okay. Example D. We have a sample of birth weights in ounces: 103 ounces, 106 ounces, 48 ounces, 96 ounces, and so forth. We want the proportion of birth weights over 100. So it may help to arrange these in order from smallest to largest. So let's do that. That's 48. Let's see. I guess the next one is 85. And then we have 96, 98. 103. 104, another 104, 106, 1, 2, 3, 4, 5, 6, 7, 8. We have 2 left. 110 and 117. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So proportion of birth weights over 100. So we have 1, 2, 3, 4, 5, 6 out of 10. And if we reduce that, 6/10 reduces to, by top and bottom by 2, reduces to 3/5. And as a decimal, again, we can think of a fraction bar as like a division bar. This fraction 3/5, you can regard it as 3 divided by 5, or 5 divided into 3. 5 and 3 goes 0. Add a decimal point to 0. 5 and 30 goes 6 times. 6 times 5 is 30. Remainder is 0. So it's, as a decimal, it's 0.6. And then as a percent, we can move the decimal point over 2 places. We need to add an extra 0 here. It'd be 60%. The mode of most frequently occurring, well, we have 2 at 104. So the mode is 104 ounces. The median, that would be the average of the 2 in the middle. If you have an odd number of birth weights, it would be the one in the middle, but we have an even number. So if the fifth from, we have 10 birth weights, 10 divided by 2 is 5. So the fifth from the smallest, 1, 2, 3, 4, 5, is 103. And the fifth from the highest, 1, 2, 3, 4, 5, is the 104. So the median is going to be 103 ounces. So 0.5 ounces. The median. So it's the average of the 2 in the middle. 103 plus 104 divided by 2. 207 divided by 2 is 103.5 ounces. The mean, we have a formula for the mean. It's for the mean of 10 numbers. It's the sum of all the numbers divided by the number of numbers. This Greek letter capital sigma means sum. So this is sum as k goes from 1 to n of xk all over n. So it's the first score, the first birth weight, plus, so it's x1 plus x2 plus x3. So x1 would be the first birth weight, x2 is the second birth weight, x3 is the third birth weight, and so forth. Plus x4 plus x5 plus x6 plus x7 plus x8 plus x9 plus x10 all over 10. So this is going to be, we can put these in any order. I'm going to put them smallest to largest, but you can use the original order if you want. So it's 48 plus 85 plus 96 plus 98 plus 103 plus 104 plus 104 plus 106 plus 110 plus 117 divided by 10. Okay, so if we add the last digit 8, 5 is 13, 19, 27, 30, 34, 38, 44, 51, carry the 5. I just double check that. The last digits, we have 8, 5 is 13, 19, 27, 30, 38, 44, 51. Carry the 5. And then 5 and 4 is 9, 17, and 17 and 9 is 26, 35, 36, 37. Put down the 7, carry the 3. Double check that. 5 and 4 is 9, 17, 26, 35, 36, 37, and 3, 4, 5, 6, 7, 8, 9. I get 971 over 10, which would be 97.1 ounces. And the mid-range, the smallest plus the largest divide by 2. So the smallest birth weight was 48, the largest of 117, and divide by 2. So this is going to be 165 divided by 2. It's going to be 82.5. Okay, the mid-range, that's the sort of halfway between the largest and the smallest. So the mean, median, mode, and mid-range are all what's called measures of center. Okay, outlier would be a number that's very different from the other numbers. And if we look at, again, arranged from smallest to largest, we see there's a big gap between the smallest and the second smallest, a big gap between 48 and 85. On the other end, there's not such a big gap. So it looks like there's an outlier of 48 ounces. So just looking at the data, it appears to be, the 48 ounces appears to be an outlier. Later in the course, we'll use more precise methods of determining outliers. Outliers are important because they might be typographical errors. They might be from special circumstances, such as a premature baby, and they might affect our summary statistics. Some outliers affect some statistics more than other statistics. The median is not so much affected by outliers. The median is said to be resistant because it's usually not affected by outliers. The mean, the other measures of that we looked at would be affected by outliers, more likely to be affected by outliers. The mean, median, and mode would be more likely to be affected by outliers. The mean, median, mode, and mid-range are all what's called measures of center. Measures of center or central tendency. Later we'll get into measures of spread that measure how spread out the data is. Okay, so just a little bit about the relationship between sample statistics and the population parameters. Generally, we'll be computing sample statistics like the sample mean, the sample proportion, and later we'll get into other statistics, sample standard deviation, sample correlation coefficient. But these, usually the sample statistics are based on data from a sample of a few hundred or a few thousand people, and they're estimates for the unknown population parameters. So the sample mean x bar would be an estimate for the unknown population mean mu, and again, usually the sample mean would be based on a sample of a few hundred or a few thousand people, whereas the population mean is usually not known, but it would be the mean for in the population of millions of people. So the sample mean is a sort of an estimate for the population, for the unknown population mean, and likewise the sample proportion p hat is an estimate for the unknown population proportion p. Some books use the Greek letter theta for the unknown population proportion. Usually the Greek letters represent the unknown population parameters. So the mean, Greek letter mu, lowercase mu, standard deviation, which we'll get into say more about, the lowercase Greek letter sigma, population proportion p or theta, and the correlation coefficient, which we'll say more about later, the Greek letter rho. Okay, so that concludes this presentation.